Hello, everyone. My name is Reid McClain. I'm a hardware engineer with Intel, and I'm here to tell you about the LTPI Reference Implementation. Shen had mentioned that earlier as a contribution. This actually is a presentation by Casper. I'm sure many of you know Casper. He wasn't able to make it, and so I volunteered to give this presentation for him. Okay, so just a quick agenda. We'll do a quick DC-SCM LTPI overview, LTPI LVDS Tunneling Protocol Interface. I'll talk a little bit about the spec development, the history of the spec, and then go into the details of the reference implementation that Intel provided. Talk a little bit about some of the details, the system test and unit test, and a call to action. Okay. Okay, so yeah, as I mentioned, LVDS Tunneling Protocol Interface. As you can imagine, the pin count, the pins are very precious, so we wanted to use a minimum number of pins and get the best bang for our buck. So the LTPI interface uses a total of 8 signals. It's a LVDS, so differential, clock and a data in each direction, source synchronous. The current implementation that we have, we're showing a demo over in the Experience Center that's running at 400 megabits per second. Certainly we could run faster than that, but that's is going to provide us, we believe, plenty of bandwidth. So in addition to that, with the LVDS, we get you're going to have improved signal integrity versus a single-ended. And this allows that, there's AC coupling with LVDS, so different FPGA vendors, different implementations might have slightly different voltages on the LVDS, so the AC coupling helps with the with the interoperability. The LTPI is it's basically it's the pathway for the BMC to control the HPM module. So the type of traffic that goes over LTPI is, so you can imagine it's mostly control and status. So register accesses are encapsulated and sent over LTPI. But in addition to that, we wanted to, fit more functionality in there. So we basically made separate channels within LTPI. So there's a general purpose I/O that can go in both directions. There's high latency and low latency GPIOs. We also encapsulate, and this part is programmable, so you can implement this, sort of customize it, if you will. So you can embed, say, a number. I'll say 6 is what we're currently doing. I2C channels, so they're encapsulated over LTPI. And then we also have UART channels, and then, of course, the data channel that I mentioned. I mentioned a high bandwidth. Yeah, we're currently running at 400 megabits, but current FPGAs would not have a problem running at a gigabit. Yeah, there's some of the features are scalability and flexibility. Each design, you don't have to, you're not fixed on the number of I2C or UART channels. You can customize that. Yeah, and then another thing on interoperability is the link training capabilities and exchange protocol allow you to operate at different adjustable frequencies, I'll say. Okay, so this is just a slide on kind of the history of the LTPI spec development. So in early 2021, Intel came to OCP with this proposal for an LVDS interface. And then the OCP community over the next year plus had input into the spec and made good improvements, and sort of came to an agreement. And in mid-2021, DC-SCM 1.0 had the initial LTPI specification. Last year at OCP, Intel, Lattice, and GoWin all had LTPI demonstrations. And then basically earlier this year, Intel made the contribution for the LTPI RTL reference code. And then this year, if you guys haven't already seen it, I encourage you to go to the Experience Center, and you can see. So the improvement this year in the demo is that we have an Intel CPLD on one end of the LTPI interface, and a Lattice CPLD on the other, so thus showing the interoperability multi-vendors. Okay. All right. So some details about the RTL contribution. It's a Verilog source code to basically implement the SCM side and the LTPM side. I'm sorry, the SCM side and the HPM side. The source code is released under MIT license. Included in there is a example project file for Quartus for a Max 10. But again, as we can contribute other devices as well. There's also pretty good simulation support, LTPI unit tests. I'll talk about that in another slide. User guide with details, as much detail as you want to go into about the implementation and how to build the IP and run the tests. Okay, kind of diving down into the RTL details. Here's a couple block diagrams. So you can see on the left is the LTPI top controller. So this would be what's instantiated on the SCM. And on the right is the LTPI top target, and that would be on the host processor module. So yeah, actually I can go to the next slide because there's some detail on each of those. Okay. So the LTPI top controller module has instantiates a PLL. The main difference between the controller and the target is the I2C target. So the BMC over I2C will talk to the SCM FPGA through that interface. That traffic comes out as Avalon memory map traffic and is routed to a MUX. If that read or write is targeted for the host processor module, it is steered into the management LTPI top module, and then will be encapsulated and sent over LVDS to the HPM. And then the target looks very similar. Of course, there's no I2C target here. The data would be received on the LVDS channel and then unpacked, and and then whichever traffic this is, if it's a control packet or whether it's UART, I2C, et cetera, is decoded in the management top module. And then finally, this just shows that the LTPI top management LTPI top module is shared between the two. Okay, the control and status registers. The control and status registers were implemented with system RDL. So what that means is that the registers are described in just in a text file, in an RDL text format, and they are compiled with Peak RDL. It's an open source compiler. And the nice thing about that is it'll spit out your RTL, spit out includes files, And it just makes it really easy if you want to customize, put some OEM-specific registers in there, you want to make some changes here or there. It's pretty straightforward. You're just modifying text files, and it will spit out RTL. So. The other part I want to talk about is that the LTPI IP is highly configurable. So I'd mentioned the various data channels. Each one of those you can enable them or disable them. They're optional. And you can also modify the number of channels that are supported. So it gives you quite a bit of flexibility. The one I wanted to touch on is the mailbox. So the data channel by default only supports a single outstanding transaction, and if you would like to support multiple outstanding transactions, then you would enable the mailbox. It takes a little bit more logic, but it gives you some more flexibility. Okay. Included in the contribution is simulation support, and the simulations were written in SV Unit, and they can be ran using either VCS or Model Sim Questa Sim. You can see there's quite a bit of test coverage there. All the new code is 100% test coverage. There's a few modules that are sort of, just IP, like, the CRC, 8B10B, encoder, decoder. Those don't have full coverage, but they're well-tested pieces of code. Okay. So as I mentioned, the demo that we have is implemented in a Max 10 FPGA. Intel's new data center platform management FPGAs, Agilex 5 and Agilex 3, will be available soon, and these are ideal for use cases like LTPI. These will be low-cost devices, and we will very soon have LTPI support on these devices as they become available. Okay, yes, the LTP IP is now on the OCP GitHub. The original drop was a zip file. Of course, being available on GitHub is going to make issue tracking a lot easier, and then it's obviously the reason we want to do that is we want others to contribute, and GitHub is the way to do that. Yes, and we will, multiple CPLD vendors and different FPGA families, as I mentioned, support. Okay, call to actions. Adopt LTPI IP in your designs. Innovate with LTPI IP, and download, make contributions, give back to the community, and we can all benefit from our shared experience. There's the link to download on GitHub, the project wiki link with the latest spec, and the mailing list. So that is the presentation. Let me know if you have any questions. Thank you. Oh, we have a question. Sorry. It's on.
UART and I2C have been defined peripherals for LTPI, but my understanding is the I2C doesn't support multi-initiator or clock stretching. Still another year went by. So I'm just wondering, is anyone actually working on improving those things or adding new peripheral types at the far end?
Okay, so I didn't quite catch it. It's which feature on I2C?
Well, I mean, LTPI tunneling only defined two different types of peripherals, like a UART and a very basic I2C controller that can't do things we need, like MCTP.
It doesn't support NCTP. Good question.
It doesn't support multi-initiator or clock
G-
stretching or
Gotcha,
anything.
gotcha. Okay, so I will admit I don't know the answer to that question, but I will get back to you on that. So I will try to provide an answer. So maybe I could get your afterwards. I can get your contact information.
Just wondering if people are contributing additional peripheral types or anything, or is it just build your own?
Yeah,
if you don't like those two peripheral types.
I don't know, but I will try to find out. Okay? Thank you.